For most of human history, our drive to explore has been physically bound to a single, fragile sphere of rock. We observe a universe populated by hundreds of billions of stars and naturally seek to push past the upper layers of our atmosphere, but the wider cosmos is heavily pressurized and deeply hostile. Near the galactic core, stars are densely packed and volatile. When massive stars reach the end of their life cycle, they detonate and release gamma-ray bursts, shockwaves of high-energy radiation that sweep through planetary systems, sterilizing them. This map of the Milky Way illustrates the specific regional parameters required for biological survival. Between the violent radiation of the inner core and the element-starved outer rim, the galaxy maintains a narrow, functional, safe zone. Our solar system is located exactly within this band, sitting between 6,500 and 26,000 light-years from the galactic center. We exist in a pocket of space, positioned safely out of range of the most lethal stellar detonations. The physical parameters that protect us from cosmic extinction are the same factors that isolate us within the dark. Looking outward from this quarantine, astronomers target exoplanets like Gliese 832c. Situated in the constellation Gliese, it sits approximately 16 light-years away from Earth. It is a massive super-Earth equipped with a dense atmosphere. Because of its proximity to its host red dwarf, it is likely tidally locked, meaning the planet's rotation keeps one side constantly baked by stellar radiation while the other remains frozen in permanent darkness. Despite these extreme rotational mechanics and heavy cloud cover, thermal modeling indicates the boundary regions between the day and night sides maintain average temperatures capable of supporting liquid water on the surface. If that water continually interacts with carbon-rich minerals expected in the soil, the environment mirrors the exact volatile chemistry of Earth's early billions of years, just before the first biological cells took physical shape. This creates a unique physical paradox. In the grand geometry of the galaxy, a distance of 16 light-years is incredibly close, yet for human biology, crossing those 150 trillion kilometers remains a physically insurmountable abyss. To bridge the distances our bodies cannot survive, we build mechanical extensions of ourselves. Inside sterile terrestrial facilities, engineers construct highly advanced robotic avatars designed to operate in environments that would instantly destroy organic tissue. The Perseverance rover represents the peak of this remote mechanical evolution, outfitted with 23 specialized cameras, geological lasers, and systems designed to pull breathable oxygen out of a carbon dioxide-heavy atmosphere. It navigates the Martian surface as a proxy for human scientists. Evidence gathered by these sensors has overturned the long-held assumption that Mars lost its entire water supply to space. Most of that volume remains trapped within the planetary crust. This diagram breaks down the specific isotopic ratio that proves the trapped water hypothesis. As the planet evolved, lightweight hydrogen atoms easily evaporated into space. Meanwhile, heavier hydrogen isotopes known as deuterium sank downward, bonding with oxygen and locking the water into hydrated minerals deep in the soil. In Jezero crater, these mechanical proxies are drilling into ancient, dried delta deposits to isolate fossilized remnants of early biology. We are pushing these mechanical extensions even further out to Titan, Saturn's largest moon. Hidden beneath a freezing, hyperdense atmosphere, Titan features a strikingly familiar geological landscape, complete with sprawling dunes, rivers, and vast liquid lakes of methane. To navigate this terrain, NASA designed Dragonfly, a nuclear-powered octocopter engineered to fly through conditions that plunge to $-179 circ text C $, relying on a compact radioisotope generator to keep its systems from freezing mid-flight. This infographic illustrates exactly what Dragonfly is hunting for. Telescopes recently identified text C 3 text H $2 or cyclopropanothene suspended in Titan's atmosphere. Its unique cyclic structure allows it to easily react with other compounds, forming the chemical backbones necessary to build nuclear bases, the direct structural components of DNA. Operating these machines exposes a hard operational boundary. When an engineer sends an instruction from Earth, it takes up to 30 minutes to reach Mars and well over an hour to reach Titan. Because of this delay, Dragonfly must fly autonomously. Our sensors can physically survive the farthest reaches of the solar system, but our real-time control is strictly tethered by the speed of light. The speed of light functions as the fundamental geometric framework that dictates how space and time interact. This chart tracks the velocity of protons propelled inside a particle accelerator. Despite massive amounts of kinetic energy being injected into the system, the velocity line flatlines exactly at 299,792,458 meters per second. Nothing with mass can ever cross that threshold in a vacuum. Particles can bypass this rule locally when they move through a specific medium. When radioactive particles travel through water, they outpace the localized speed of light for that medium, triggering a visual shockwave known as Cherenkov radiation. While we can observe these localized optical booms in a reactor pool, the ultimate vacuum speed limit of the cosmos remains intact, keeping us within a vast cage of time and distance. Yet, deep within quantum mechanics, phenomena exist that appear to bypass these spatial restrictions entirely. The primary anomaly is quantum entanglement. When two quantum particles become entangled, altering the physical state of one instantly synchronizes the state of the other. Whether they are separated by an inch or a million light-years, the change happens with zero time delay, directly challenging our localized understanding of physics. We observe similar rule-breaking on a macroscopic scale. While no single object can move through space faster than light, the observable universe is currently 93 billion light-years across. This means the fabric of space itself is expanding outward at a rate that exceeds the universal speed limit. This elasticity in spacetime leads physicists to calculate the theoretical existence of wormholes' gravitational anomalies that could fold the geometry of the universe, allowing a traveler to bypass billions of light-years of distance entirely. By examining these physical constraints, from the chemical dust of Mars to quantum synchronization, humanity is defining the exact mathematical limits of our local universe.